cyclic voltammetry, you ramp up or down, but you ramp up and down and up and down as many times as you want, or down and up, down and up. You can go whichever direction is appropriate. And what you get is a current as a function of the applied potential, and I'm showing it getting more negative as you go that direction. So, okay, your recording, is that for Drew?
And Willow.
Yeah, okay, but I thought Drew said something about sending an iPad.
I have an iPad, but I saw that I have Drew's iPad.
Okay, I don't care as long as she
It
said
doesn't
at
matter.
one point she couldn't get things loaded. Anyway, so before I draw the picture, let's think about this. If we go up in potential, that means that we're going to eventually get more positive than something in solution, and we're going to cause it to oxidize. And then when we go down in potential, we're going to get more negative than it, which will cause it to be reduced. And then we do it all over again just for fun. And so, so we expect to see something get oxidized and then reduced, or reduced and then oxidized. And so the kinds of things that you get are what we used to call duck plots. You get something that goes up, and then it levels off, and then you reverse the potential direction, and they tend to look something like that, which we said, oh, they're just drawing pictures of birds. And we need to talk about what's actually happening, but first let's label some pieces. So that's a cathodic wave. Remember, I'm getting more negative first. So I started out someplace and got more negative, and then I went positive. So that's a cathodic wave, which means we have reduction occurring. That makes this an anodic wave, which of course means we have oxidation occurring. You'll note that the current goes up, sort of plateaus, and comes back down. What causes that? So remember what's happening in voltammetry. We've got to get mass transport from the bulk of the solution to the electrode surface. We're not stirring in cyclic voltammetry. And so the mass transport is primarily diffusion. Remember, in the Nernst layer, certainly it's diffusion. So the only way for our analyte to get from where it is to the surface of the electrode is diffusion. And we're ramping the applied potential actually fairly quickly relative to diffusion. And so, although you start off with a current that can be maintained because the analyte diffuses to the electrode surface fast enough, at some point you get to a potential where diffusion can't keep up. And when you pass that point, the current drops off because all of the analyte at the electrode surface is now gone, and you can't get it there fast enough to maintain the current that you had. So that's what's happening both here and there. in the polarography stuff that we looked at last time, it could keep up. You just move the potential slowly, and diffusion could always keep up.
Could you think of like the graph of the cyclic voltammetry, like the line starting from the top is moving through time?
Yeah,
Okay.
so this point and that point are the same time period. Yeah, so as you were doing this, you were getting that current. Then you came down here and did that. So you could string it out as a function of time, but typically they just plot it back on itself because you're simply changing the applied potential. It's coming back, well, in our case, it's going more positive as it's coming back this direction.
So these graphs represent the same thing happening but different parameters?
They're at the same time. So this is what's happening to the applied potential over time. And as the applied potential varies, this is the current that you get from it.
But it's the same thing happening, just two different graphs of this.
It's at the same time.
Okay.
Yeah. Let me clean up the graph if I can do that without having to erase everything again. This is called EPC, or really that point is called EPC. It's the potential at the peak of the cathodic wave, and this is EPA, the potential at the peak of the anodic wave. And what we want to find so we need to figure out where the baseline of this is, and so it's something like this, and that is the current PC, and then the baseline for this one is not the same baseline. In fact, in this particular graph, we're going to have to make up our baseline. We do not have good data to determine a baseline here. So let me do a different color. Be something like that. IPA. Yeah, free.
What do those things stand for? EPC, EPA?
Potential, peak anodic. Potential, peak cathodic.
Okay.
Current at the peak of the cathodic.
Okay.
So.
So the line through the middle is like an average?
No, it's the baseline.
It's just wherever you
So
started.
so you're extrapolating this over,
Okay.
because that's your baseline. Up here, that green one is pretty much invented. It's a horrible baseline. We don't really have a great deal of data to go to generate a baseline. Hopefully your graphs don't actually look like this picture, that you actually have more of a baseline, like maybe this black line. If the black line did something more like that, then the green line makes more sense, and we'd actually be able to measure a baseline and get the data we want. So for a reversible reaction, and reversible reactions are defined as reactions that can be reduced and oxidized, or oxidized and reduced. That is, the reactants or products are fast enough to maintain equilibrium concentrations at the electrode. Let's say reaction is fast enough to maintain equilibrium concentrations at the electrode. And the way you decide if this thing is actually reversible is the difference between the peaks, which we will define as EPA minus EPC, which should be given by 2.22 RT over NF. Turns out to be something like 57 millivolts divided by N. So if the difference between the peaks is about 57 millivolts divided by the number of electrons involved in your process, you've got a reversible reaction. So if N equals 1, you're looking for something close to 60. If N is equal to 2, you're looking for something close to 30 millivolt difference between them.
57.0?
57.0 is what that math comes out to be. We take it generally to be 60. If it's close to 60, we're good. It's not reversible if delta EP is greater than 57 divided by N millivolts. That is, the peaks get further apart, the less reversible it is. A second parameter that will help you is that if IPC is equal to IPA, it is reversible. So you have two ways of knowing if this reaction is reversible.
And not, if it's less than 57 divided by N,
It should never be less than 57.
so it's only 57 or greater.
Mm-hmm. Yeah. Within experimental error. So. Okay, so what in the world is a non-reversible reaction? Well, what would happen if you reduce something and then that something reacts with something else in your mixture, so that now it's no longer available to go back to the oxidized thing you started with? That's an example of a not reversible reaction. So you electrochemically generated something and it reacts with something else or falls apart into something else, etc. And you end up not being able to maintain equilibrium concentrations because the thing isn't there anymore. You end up getting duct plots that look something like that. If that's a very fast sweep rate, because we can change how fast we're sweeping the rate. But actually, let's make this a little deeper. So this is fast. And if we go at slower scan rates, we're going to get basically the same one on the top, but we will get less and less there because the product we're making in the first redox portion of the cyclic voltammogram is having more and more time to do the subsequent reaction.
This speed is based on how fast you take scans or how fast the reaction is occurring? Or
Both.
Okay.
So the scan rate, we are scanning, each one of those lines represents some scan rate, and I was getting slower and slower as I drew them. So the black one is the fastest one, and the green ones are getting slower. That means it takes more time to go from this, let's say there's E1 half. It takes more time to go from here to there which is the same E1/2 going the other direction now. So if it was reduced here, it's going to be oxidized there. But the slower I go, the bigger the time interval in here is, the more time the stuff I'm making had to get destroyed. And we can actually, conceptually, we could measure, okay, let's figure out where our baseline is, different color. So we have a baseline here. We can measure that distance, then that distance, then that distance, then that distance. And if we make a graph of those, it should look something like a kinetics plot. Because it's how much of my product is still there to go back and be reoxidized. In fact, that's exactly what we do when we use this to get rate constants, which is a piece that it is good to do. So, so one thing is we can get rate constants. We can use cyclic voltammetry to determine reversibility of a reaction. And we can at least use it to try and get clues about what subsequent or competing reactions might be there. And sometimes what you find out is, hey, the thing that it made is also redox active, and so you don't ever get this peak, but you get another peak someplace else. So clearly the first reaction isn't reversible, but maybe the second product is reversible. And you can so you get all kinds of interesting things from this. So what I described here would have been something like A does some electrochemistry and gets to B, and then B becomes C. And we can figure out the rate constant of that reaction by varying the sweep rate, Alex.
So when you vary the sweep rate, would EPA change?
Yeah. Actually, they may both change.
Okay.
And if you go fast enough, like the black one I drew, sort of looks like it's reversible. And it might be. It may be that if you go fast enough, you actually made something and used it up again before it had a chance to do anything, depending on what K was. But then as you slow down, it gets less reversible because now you're giving K more time to operate on B. And it just gets worse and worse and worse. So, yeah, so frequently by speeding up the sweep rate, you can get it closer to being reversible, or maybe even make it reversible. So, yeah. Okay, that ends the chapter. The oral for cyclic voltammetry is open. I think I have 2 slides for you yet to look at. So we'll take a quick look at those. So the first ones are a summary. And since you have this in front of, you, is that bright enough to see? So it's a summary of a whole bunch of pieces that we looked at. So classic or linear polarography, there's the sweep program for the potential, and that's the outcome that you get. And remember, this was with the dropping mercury electrode, so you get this horrible noise. And then we do current sampling. These two are really identical, it's just you can't see the noise anymore. But it's still there, unfortunately. You just can't see it. So you think you have wonderful data. And then this is one of the first, this is normal pulsed polarography. Remember, normal usually tells us this was the first one that was thought of or discovered, and then everything else is different from normal. And so we did not talk about this, but a pulse program where you jump up and then come back down all the way, and then jump up higher and come back down, and you get that. And you see detection limits. These detection limits vary a little bit from what your text said. What I reported earlier was what your text actually said. The last one we did talk about, why it works, differential pulse polarography. We did not specifically talk about fast sweep polarography, but basically it's half of a cyclic voltammogram. Move things fast enough that you get the top part of the duck plot. And then just bop the voltage back down here and do it again, is what this suggests. And there we just talked about that. We did not talk about alternating current stuff, but we did talk about the last one, which is the stripping voltammetry.
What does sweep mean?
How fast you're moving the voltage. So in none of these are we keeping the voltage at a single value. We sweep the voltage from some value to some other value and look for, did we cross a potential where oxidation reduction can happen?
Okay.
And if we didn't, it was boring. But if we did, then interesting things are happening and we can do all the stuff we've talked about. Okay. So
would,
go ahead.
sorry, would sweep have like units?
Pardon?
Does sweep have like units, or it's just?
Yeah, it's volts or millivolts per second or per minute, how fast are you gonna go?
Okay.
So we're going to be sweeping it at millivolts per second, I think is the units we're going to use. So we're going to say, run this, change the voltage at 20 millivolts per second.
And when it
Go.
changes it, then it'll like plot a point too?
It will apply this voltage and put that graph on the screen,
The duck plot.
the duck plot.
Okay.
Yeah, although it may be a hummingbird plot. You'll have to identify your bird, Alex.
How long does that typically take to get the whole duck plot?
Oh, let's think, what kind of range might we have? Say we went from +1 to -1 and back. So now we have 2,000 millivolts. Let's make an easy number. Let's sweep it at 100 millivolts per second. That took us 20 seconds, didn't it? Or was it 200 seconds? Yeah, it was 20 seconds. Took us 20 seconds to do this. So we're talking a few minutes to do a series of experiments. So, yeah. If we were sweeping at 20 millivolts per second, that range would have taken us, 200 seconds, 3 minutes to do. If you go down to 5, bring a good book. Right? So,
Do you do multiple duck plots to?
yeah, often you do maybe 2, but you have to be careful. As soon as you start doing this, you're messing with concentrations at the electrode surface. And if things aren't reversible, it's going to mess with it significantly.
So these are all different types of voltammetry and polarography. Do you pick like certain ones for
Yeah, you pick the
certain-
one that is going to give you information you think will be helpful.
Okay.
So if all you want to know is the concentration, I would not pick cyclic voltammetry. I'd pick some kind of polarography.
Okay.
In fact, I'd probably pick a pulse polarography. If all I wanted to know was, can I drink the water? Is there too much copper? Is there too much lead? Some kind of pulsed polarography is probably the way to go. If I'm trying to figure out kinetics, cyclic voltammetry is a wonderful thing. to start looking at, and none of the others will help. That means that cyclic voltammetry might start giving us mechanistic information that all the others can do is say, hey, this is the current. They're used to do quantitative work.
Okay.
So when they test water for different levels of contaminants, is that the types of things they're doing, or is there different ways?
Oh, sure. This is a really effective way, if you are set up to do it, to test water. I mean, it's fast. Done, okay? Computer already did the calibration curve, it's over. Write the letter, tell them to stop drinking the water. Think Flint, Michigan. Are you from around close enough that you know the lead stuff happening in Flint, or that happened in Flint, and now we wonder about all the other communities in southern Michigan because they all grew up in the same era and system. So yeah, you need to be able to very quickly run through maybe thousands of samples to find out what's going on. This is a fairly quick way of doing it. And there are other techniques too. So, and it all depends on what has been approved by the EPA. So what you're allowed to use to do this determination. Okay, one last piece to wrap up the electrochemistry, and that is always try to think outside the box. So most of you, I think, are headed onto something after Goshen College where you're going to continue furthering your education. If that happens to be graduate school kinds of things, you really want to think outside the box. So one of the problems with electrochemistry is that duck plot tells you all kinds of cool things about potentials and reversibility, and we can get rate constants, and we have no clue what C is, right? We may not even know what B is. We might, okay, it's a little closer to A, so we can do some guessing, and we can figure out how many electrons it was, so maybe that helps. We'd have to go back to our organic textbook and start figuring this out. Wouldn't it be nice if we could couple that electrochemistry with some other spectroscopic technique that would allow us to get information? And that's what this was an article that I found. It's ancient now, but it gives you ideas of, okay, so they use like window screen. It was expensive, it was gold window screen. And they sandwiched it between two glass plates and said, let's make that my electrochemical cell, and I'm going to stick it in a UV-Vis spectrometer. Think our UV-Vis spectrometers. Click, entire spectrum's now recorded. Instead of a scanning one where you'd have to wait a minute or something to get those. So boom, that quick you've got the whole spectrum. You just took a spectrum of B, because you can tell that thing to take spectra, start with A, oh, now it starts becoming B, now we have a UV-Vis of B, and we can start figuring out maybe what this is. Because maybe if it's a metal complex, we can see something happening. Or you can watch, as in this particular case, they're watching this stuff go away. Well, why do you have to do it with just UV-Vis? Why don't you put that electrochemical cell in an infrared spectrometer? Oh, now, okay, we have to go a little slower. The infrared spectrometers record things a little slower. But now we can get vibrational spectra that you all know from organic chemistry. You can start to assign, and you can get clues on what this is. Could you rig it up so you can put it in an NMR? That's going to be... I see some potential challenges here, but you have to think outside the box. How can I get information that will help me? All I'm doing for you here is laying down the tools. This is how an instrument works. This is the kind of information you can get. Somebody had to figure out that it would be really handy to put a mass spec on the end of a GC. You can be the next somebody to figure out what kinds of stuff like that needs to happen. Go for it, Jonathan. Okay, that's the end of the chapter. Let's hit chapter 24. This is the chapter we're actually supposed to be talking about this week. So it feels like maybe we're catching up a little bit. The 12th, just think a little bit ahead. The 12th is the day of the symposium. Classes are formally canceled. I have no commitments that day. Do you want to do anything to keep trying to get ahead, or do you have, I see at least one head shaking no, that you've got enough commitments involved? Okay. Okay, just thought I'd put it out there in case. So, we're starting the last section of the course now, the broad topic, and that's spectroscopy. Spectroscopy is simply the interaction of light with matter. An awful lot of this is going to be review, so I intend to go rather fast. There's a wave. We're talking about waves because we've got electromagnetic radiation, that is light, all light, doesn't matter what the wavelength is an oscillating electric field and an oscillating magnetic field perpendicular to that. I don't think I can do that. You know, it's like the patting your head, rubbing your belly, or whichever way it was, trying to do a wave this way and a wave that way at the same time. Practice it. It'll come out handy somewhere for you. There,
And then you just have to walk forward. If
there you go. So 3 has it down.
Great.
So that's why it's called electromagnetic radiation. Remember, it's got both oscillating electric fields and oscillating magnetic fields at the same time. So we talk about things like the wavelength. The amplitude. And all of this is stuff that you've heard before. Nu is frequency, usually given in 1 per second, which is a hertz. Or sometimes expressed, I guess, let me do one more. Sometimes expressed as cycles per second. Brady?
What symbol is that for frequency? Is that a V
It's
or
a,
a
it's a
D?
nu,
A nu.
Greek letter nu.
1 over S?
1 over seconds is a hertz.
Cycles per second.
So
It's like a curvy V.
we have to distinguish
That's a-
that cursive looking nu from a clearly non-cursive looking V, which is velocity. How fast is the wave traveling? Which is distance divided by time. Velocity is independent of medium. Whoops, wrong. Got it. I jumped a line. I was looking at that and saying that can't be, that's not anywhere near true. This is independent of medium. So the frequency doesn't change, but the velocity and the wavelength are both dependent on the medium. So when light traveling through air enters water, its wavelength changes. Its frequency does not change. Because its wavelength changed and frequency did not change, that means its speed had to change. Really, it's probably the other way around. We have measured the speed. We know the speed changed. The frequency did not change. Therefore, the wavelength must have changed. So we know that velocity is equal to frequency times wavelength. For light, we usually change that to a c. So all of this is true of all waves, but for light we typically put c in, which is the speed of light, which you may recall from physics someplace is 3 times 10 to the 8th meters per second in air. Or vacuum. Unfortunately, as chemists, we frequently use something called nu bar, which is a wave number. Do you remember where you've seen wave numbers recently, Brady?
No.
Anybody else remember where he's seen? He's in organic chemistry now,
In organic chemistry.
but where in organic chemistry?
IR?
IR, yeah. These are reciprocal wave numbers. So, or reciprocal centimeters. Nu bar is equal to kV, where nobody ever carries that one in their head. Energy is h nu, frequency. It's also hc over lambda and hc times nu bar. And written this way, you can begin to understand why nu bar ever came into an existence, which is a bane to most of us. But it's because, hey, 1 over the wavelength, which is nu bar, right? This starts to be a more convenient way of expressing things, particularly if you have to type it by hand or typeset it, old style typesetting.
I'm confused on wave number. What's that equation?
This
Wave
or
number
that?
times 1 over the wavelength, or the wave number
No,
is?
it equals. So this was the definition of it.
Oh, okay.
Mhm.
So, when you said wave number equals kV, that looks like a.
Yeah, and you'd have to figure out what the constant is. I don't think it's,
Is that a V or a nu?
it's a nu.
Okay.
Wait,
Yeah.
nu equals K.
Nu bar is equal to K nu.
Oh. And then E equals H nu?
Yes.
And then
Yeah,
H
you know that,
nu.
everything down here you know already.
Planck, is that Planck's constant?
Is what?
Planck.
Yeah, Planck's constant, H. 6.626 times 10 to the negative 34 joules seconds, right? You remember that.
What's K?
It's a constant.
And you said
Nobody
that's a
ever- okay.
nuisance to us? Okay, great.
Whoops, didn't mean to get rid of that part.
Oh,
Oh, I managed to get rid of nu bar as well. You did not deal with this in GChem, but
What's
you
this?
dealt with the other
What's
in
that
GChem.
called?
Right, all of that should be,
Nu?
in fact, you dealt with that in high school, almost certainly.
It's
You
frequency.
talked
I
about
just like-
atomic spectra or something and had to do something or convert wavelengths to frequencies.
Would it be bad to just use F?
For frequency?
I don't care what you use.
Okay, I'm gonna change all
You-
of
If
this.
we
have-
write that on a quiz,
You
will
have
knock us for
the
that?
English alphabet, the Greek alphabet, Chinese characters, Korean characters. I don't
should
care what
switch
you
to
use.
Korean.
As,
Okay.
as long as it's a defined symbol, I don't care what symbol it is. This is a picture of an electromagnetic spectrum. And we'll start over on that end. So we as scientists, chemists in particular, pay attention to different regions of the electromagnetic spectrum. So when you start down here, these are long wavelengths. So we're going to go long wavelength to short wavelength. Long wavelengths is what color?
Um,
Blue.
gold, no,
Red.
red.
They're red, although this is way longer than red. This is out in the radio frequency. We're talking about meter-long wavelengths, radio waves. And we use that region to do NMR. This is nuclear spin transitions. You talked about this in organic, where you say, oh, hydrogen has a spin of 1/2. That means it has two spin states, a positive 1/2 and negative 1/2. And we're going to spin flip them by shining radio frequency light on it. And that's the right gap to make it go from spinning this way to spinning that way. You move to slightly shorter wavelength, so instead of multiple meters, now we're talking multiple centimeters. I think that's still radio wave, and we do electron spin resonance. So instead of nuclear transition, it's now spinning, flipping the spin of an electron, ESR or EPR it's often called. Microwaves is the energy to excite rotations. You may not have known that rotations are quantized in molecular things. You and I can spin at whatever speed we want up to some value before we fall over. But molecules will spin only at particular frequencies, and you can cause them to spin faster or slower. That happens to occur in the microwave range. Do you know what we use that for in our society? Yeah, I mean, it's painfully obvious where the name microwave oven comes from. You are exciting the rotational energy levels of water, and rotational energy levels tend to be very tightly coupled to vibrational energy levels. And what do you call infrared heat? I just blew it. What do you call infrared radiation?
Heat.
Okay, if I set you up just right, I could get you all to give the right answer. Yeah.
So with NMR, the spin is in the chirality.
No. NMR, the spin is the nucleus. It's the nucleus of individual atoms spinning this way or that way. And you shine radio frequency light on, and it gives enough energy to get to the next higher level, which is the other spin. That in hydrogen there's only two, carbon there's only two. So if it was spinning this way in your magnetic field, when you shine radio frequency light on, now it's spinning the other way.
But that's quantum spin and not like physical spin, right?
Right, it's not where the molecule is spinning, right? It's
Okay.
it's the nucleus rotating on its own axis.
And then ESR, it's pretty much the same thing, but the electron.
Exactly the same thing except for an electron, which also is spin 1/2.
Right. And then microwave.
Microwave is the whole molecule rotating,
Okay. So
and it
that's
has three axes
physically
about which
spinning.
it can rotate.
Okay.
It can rotate around X, Y, or Z. And so you have, if it's not a symmetrical molecule, it has three different energy level sets in rotation. Then we move to infrared, which you're more comfortable with, sort of the vibration modes, bends and stretches. And then visible, which again you tend to be pretty comfortable with. This is electronic transitions going from an electron going from this orbital to that orbital. And when it's molecular, it tends to be lower in energy, longer wavelengths. As you start looking at atoms, it tends to move to shorter wavelengths, higher energy. And if you start nailing the core electrons and moving them out, now you're talking X-ray. So that's core electrons with X-ray. And then the last one, which we only talk about in inorganic, no place else, and only briefly in inorganic, is changing the shape of the nucleus.
What is that word?
Mossbauer spectroscopy. M-O with an umlaut, S-S-B-A-U-R-E-R, Mossbauer. It's a person's name, I think. So, but it's a nuclear transition that changes the shape. So to us as chemists, we've got all kinds of regions of the electromagnetic spectrum which we want to pay attention to, and they're each individual types of spectroscopy. And then we go and try and build instruments that will do that type of spectroscopy well, because they all have problems. Like NMR, the problem is, how in the world do you sweep radio frequency? That was really challenging. And so early instruments, the first instrument I learned on was a field swept instrument. Now we've taken exactly the same magnet and made it into a Fourier transform one. We are punting completely on let's sweep the frequency. But for UV vis or IR, that was the easy thing to do. You set up a source of radiation, bright white light for UV vis, and you make a prism, and you rotate the prism, and now we can get a detector stays over here, and we can shine various colors of light, whichever one we happen to pick. And it was the same idea with infrared, except the source was different, and the detector was different. And down the road, I'm going to ask you to conceptually build different kinds of spectrometers. It's a quiz I always ask. I want to know how to build an infrared spectrometer. What components are you going to use? Because otherwise, it's very similar. NMR, not quite. We don't use a prism. We beat it up different ways and get the light to do what we want and get the molecules to do what we want. That's quantum mechanics. That's where I talk about that. So,
Dan, do you have that thing that you just posted, or that was just on the screen? Is that on Moodle?
I think it's posted on Moodle. I debated making copies, but I only have it. I don't have a hard copy of it. I only have it as the acetate thing,
Yeah.
and so it gets messed up when it goes through the copier. So, but I think I put it up on Moodle. Check it and see.
Okay.
If not, I'll try to get a copy of it
Okay.
for you. So it's a cool little sheet.
It is.
So. Absorption. So you've got a cell holder, and you've got light coming in, and that light has some power. That's the P. And it's a power subscript 0 because it's the initial power. And you get some power out after it has gone through your cell. Transmittance. Which is capital T, is given by the power that comes out divided by the power that goes in.
What's the thing in the middle?
That's your cell,
What kind of cell?
whatever kind of cell you want it to
In the
be.
body or like a...
No, does that look?
No, that's what I was
We're talking,
that's
what,
not making
we're
sense.
talking about what?
Like a cuvette where the
Yeah.
endoplasmic reticulum.
Or a flow
Great,
cell.
thank you.
Or like
Yeah.
it's the
Percent transmittance.
The reason I was thinking that is because radiation zaps, anyway.
She's the one that's
You're in a
CT.
different ballpark. We're not talking nuclear radiation. We're talking electromagnetic radiation.
She's always talking about radiation. I don't think anyone does.
So percent transmittance and transmittance, there's the definitions. We use this still on infrared. It's about the only place that I think we still use percent transmittance. Absorbance. Did I hear a groan?
No.
I don't like being confused.
Okay.
Nobody does.
I just,
Okay. Absorbance is the log of the initial power divided by the current power. These are linear, and this one clearly is not. It's a log scale. Historically, before computers took over the world, transmittance, percent transmittance was the way to go for the very simple reason of I can estimate between the marks. It's a linear scale. So it goes 0, 1, 2, 3, 4, and if it's between 1 and 2, I can estimate where between 1 and 2. Or maybe my scale goes 1.1, 1.2, and I can estimate in between. That is really challenging to do on a log scale. And so So prior to computers doing things where we now have digital data pretty easily, these were the more popular ways of recording how much light is being absorbed. And it was out, reported as how much light is making it through. Now, we do this because this has Beer's law. Absorbance is directly related to concentration, and transmittance is not. Now we can do it all digitally, so we can get our absorbances easily, and now we can use Beer's law directly. Whereas before, you would have gotten your percent transmittance, converted it to absorbance, and then done the concentration thing. Or dealt with a log. If this is linear, then that had to be a logarithmic relationship. So, we're out of time, but we'll pick up there next time.
So, what is in the cuvette then, like your sample?
Right now, there's nothing in there, but it'll be your sample eventually.
And it has a power initially, or?
No, it's the light coming in. Remember, we're doing spectroscopy.
Yeah.
We're passing light through a sample. So we have whatever your sample is in this spectrometer, whatever kind of spectrometer it is, you have some light intensity coming from your lamp. How much makes it through? The ratio of how much makes it through to how much you started with is transmittance. Multiply by 100, you can get percent transmittance.
Yeah, okay.
Flip it upside down, take the log, you've got absorbance. So, we still have old spectrometers that we don't use anymore that are in transmittance. Biology, do you still use the Spec 20s in biology for anything? I think they bought newer